Hello. Everything should be set up now. I was updating the website. I'm a few minutes late because I was added some notes to the website. So let's see. You hear me? And you see the desktop? Everything seem okay?
Yep.
Okay, great. Thanks. Okay. All right. So I'm going to download all these languages and talk some more about them. So we got languages 7 and 8. Seven's our base for understanding eight. Seven, it's a simple language like C, and eight is a functional programming language. And then we got this intermediate language that we did last time that kind of is in be. Whoops. Um, Let me see if it's up there. I thought I had it up there. No, I forgot to upload it to the web server. So let me get it from. I didn't realize I'd forgotten to upload that language to the web server. Okay, so I'll try to remember. I hope I remember after class to upload that. Okay. All right. So we got these three languages. Okay. Now the what we're trying to build up to is closures. Yeah, the closures are the thing that is the important concept in modern programming languages that makes that's one of the big differences between old-fashioned language like C and C++ and older Java and what is happening to newer programming languages. Closures aren't functional programming, but closures are a big ingredient to it. You really you can't really do much of anything that's what we call modern functional programming without the idea of closures. Okay, so these examples here, we're building up to, they use language 7e to see where language 7 kind of, like what you can do with language 7 before things kind of fall apart and you need this thing called closures. Okay, now, well, let me unzip these. Now, since the motivation is functional programming, functions are the thing that really are at the heart of this. That it's all about what can you do with functions besides just call them. And what it really means, can you treat functions as if they were like a piece of data? This is the idea, partly of the idea of what we mean by a first-class function. Can you take a function and pass it around and store it in a variable, pass it to some other function? That's part of the ingredient of functional programming is a function is a piece of data like the number 5 is, or a string is. You're used to strings being data and numbers being data and arrays being data. When you're taught to program in languages like C and C++ and Java and Python, you tend not to think of functions as a piece of data. But a real important part of modern programming is to treat functions as data. You can store them in arrays, you can send them over the internet, you can pass them around. You can, and it's a weird idea. It's not an easy idea to get to think of a function as something you pass around. Okay, and one thing we can do is we'll see examples of why it's useful to pass functions around. We kind of get a hint of that with the callback functions. We did examples that were callback, but then if you haven't done GUI programming, callback functions don't mean a whole lot. So that example is real useful if you've done GUI programming because callback functions are the event handlers. And that's an example where you have to store a function somewhere. We kind of did that example here. In a real rough case, the idea was you'd have a place to store something called the keyboard handler or the mouse handler. And then you'd have a function that you call that function and you pass it a function. There's the first class function. And it stores the function you pass it in the place where you store the handler. Okay. So register mouse, takes a function, sets the mouse handler to hold that function. So essentially it passes that it passes that function to that variable. So that's a first class function. It's been passed as a parameter to this function, and it's been stored in that variable. Then register key did the same thing. Then sometime later, somebody clicks on a mouse, and then the GUI system calls the mouse handler. Well, here's where the register is actually done. Yeah, this is the definition of the register function. Here, somebody registers as the mouse handler the squaring function. Someone registers as the keyboard handling the cubic function. Then sometime later, somebody clicks on a mouse, so the mouse handler is called. But when the mouse handler is called, it's really calling square. Yeah. See, it's an indirect, kind of an indirection. When the mouse handler gets called by the GUI system, it's really calling whatever function we told it to call when the mouse click came. When someone taps on a key, the GUI system calls the keyboard handler, but it's really calling whatever we said is the keyboard handler. Okay, that's a real. Now this goes back to the 70s. This is not functional programming, but when you start combining this is an example of a first class function. So this is why you would want first class functions. But as you combine first class functions with other ideas, eventually you need closures and functional programming. Okay, so now actually let's look at another example of let's look at another example of why you'd want first class functions. Oh, actually, if you want let's look at these. Let's go back through these three again. Okay, yeah. Here's the idea of a nested function, a function sitting inside of a function. Okay, well, actually, a function inside of a begin block. Okay, it's not a function that's not global. Okay, so this function is sitting inside of a begin block. It's not a global function. Okay, all right. Now, there's nothing weird about this. The function f is a squaring function, and I apply f to 5. That worked fine. Okay, so nested function, it just lets me define a function locally. But then if I do something a little bit trickier, okay, things can get a little bit, okay, so I want to build up to something that goes wrong. Here's the same nested function, okay? But now I take that nested function and I store it in a global variable. So now I've got a first class nested function. Okay, so I went from a nested function to a first class nested function. The function stored in a variable, then I call the function using the variable. So this is like that callback example. So this is nested, but then it's assigned to a variable, so that makes it a first class nested function. But nothing goes wrong here, okay? Now, make it a little bit more general. Here's the nested function. It's inside it. It's not global, so that means it's nested. I'm not doing first class, but I'm letting the function make use of non-local references. The function takes in a parameter z, but it refers to x and y. X and y are these local variables, okay? So I've got a nested function that makes use of non-local references, okay? So I've got three ideas so far: nested function, first class function, nested function with non-local references. Okay, now that's three ideas, but I haven't used all three in one place. Okay, so I've got the nested function, I've got the non-local references in the nested function. Okay, but I haven't got, like this case doesn't have the first class. I'm not using the function as a first class function. Okay, now combine them all. Okay, there's the nested function because it's not global. It's making non-local references. It's assigned to a global variable, so it's being used as a first-class function, and now we got a problem. And that's what we were doing the other day. Now, when we combine all three of these ideas, first-class, nested, non-local references, now we have a problem, okay? What's the problem? You build this block, and it holds the variables x and y. But the x and y are in this block. When you get to this line here, the block goes away. It's deallocated. G points to this function here. When you call G, you call that function, x and y are not there. There are no x and y anymore because this block disappeared when you got to here in time, okay? This block was created, x is created, y is created, f is created, but then f is stored in G, so we say that f escapes. So now G refers to f. The block goes away, but f doesn't because it's stored in G. But x and y go away. Their storage is deallocated. When I call G, I don't have an x and a y. Okay, so I've got a problem. Okay, when I mix these ideas, if I mix nested functions with non-local references and I make it a first-class function, I can get a problem. The function can escape from its non-local references. Okay. Okay. The function is nested, so it has possible. Now, if the function wasn't, let me download these and see. Make sure you understand, like, why it has to be all of these combined. Okay. So let me download them and go back and see. What if what's really causing the issue here? Okay. So okay, here's example 1, example 2, 3, and 4. Okay. So here's the one that causes the trouble. Okay. Now, if you got rid of this begin, this is a global function, and these are global variables. Okay. Now notice there's no notion of them going away. See, this is a global function referring to global variables. Global variables can't go away. See, once you declare them, they stay there forever. Okay. So the begin, the key about a local environment, which means you have a nested function, is that the local environment has a point where it can go away. See, local environments, when they get to their closing brace, they disappear, just like in C or Java. Okay, so, but if you don't have that, then this code is fine because everything is global. Okay, so I mean, now what do I have now? I have a global function that makes non-local references. Global function. This is now back to C in language 7. Global functions that make non-local references are okay. There's nothing wrong with non-local references as long as they're to global function. Oh, and I've got a first-class function. Notice I'm storing the function in G. When I call the function, I don't call F, I call G. So here I have if in this example now is a first-class function with non-local references. Fine, no problem. That's C. That's language 7. Okay. But if I nest the first-class function, then I could end up with a real problem. Okay. So it's okay. Now, on the other hand, let's suppose well, as we saw before, if I don't have the non-local references, yeah. Oh, if I have, yeah. Now notice that if I have only 2 out of the 3, the issues are non-local references, nested, and first class function. Yeah, first class. Yeah, the issue is nested first class non-local. Nested function that's first class with non-local reference. If I have two out of those three, I don't have a problem. The funny thing is, any two of the three is not going to cause a problem. Okay, so like when I delete the begin and I delete this, I'm getting rid of nested. So I have first class references I have first class non-local references. Then it's not a problem. Here it is nested non-local reference, but not first class. No problem. It's nested, okay? But I call the function before these variables go away because the function can't escape. There's no first class use of the function. So the function is nested inside here, and its call has to be nested inside here because I don't have anything that stores the function. So the only place I can use the function is in here where it's been defined. It cannot escape here. So if I have a nested function with non-local references, that's okay, as long as it's not first class. So I got two, but not the third one. Then if I go back to this other example, what does this one have? This has nested first class, but not non-local references. See, the function is nested, and it's first class, so it can escape, but it didn't make any non-local references, so it can't access a variable that'll disappear. See, without any non-local references, it's not using anything outside of itself. It's self-contained. See, it's a closed expression. So if I have a nested first-class function, yeah, without a local reference, since this function will be closed, again, even if it escapes, it's not escaping with a reference to something that doesn't exist anymore. Over here, when this function escaped, it escaped with a reference to something that disappears. Okay, so again, if I have all three nested, first class, non-local references, I have a problem. But two out of the three is okay. Yeah, so get rid of the nesting by getting rid of the begin here. Get rid of the let's see, this one gets rid of the escaping. It isn't first class. And this one gets rid of the non-local references, but it keeps the nesting in the first class. Okay, so you don't have problems. Okay, you need to have all three of those. Okay, but those three, that combination is really what's important. Nested first-class functions that use non-local references. Now, in the history of programming languages, lots of languages had two out of three of these. Okay, C has first-class non-local references, but it doesn't have nesting. Okay, other functions would have things like you could have nested first-class functions, but if you did, they were not allowed to use non-local references. If the compiler saw the nested function make a non-local references, the compiler would give you an error message. So you could have a nested function, okay, and you could make it first, or another possibility is the compiler would say, okay, nested functions with nested functions with non-local references are fine, but they can't be first class. So some languages would look at this and say, good, but then this would not compile. The nested function with a non-local reference is not allowed to escape. Other languages would say, okay, you can escape you can escape the nested function, but you can't have non-local references inside of it. Okay, so the languages would always make sure that you only had two out of the three. Again, C does it by having no nested functions. That was the easiest thing to do. Just eliminate nested functions. First class functions, fine. Non-local references, fine, but nothing is nested. So that meant that the non-local references are always the global variables. Since functions cannot be nested, their non-local references would always be to global variables like this would be. See, now the function is not nested, the function's global, and its non-local references are to global variables. Global variables can never disappear on you. Global variables, once they've been declared, sit there to the rest of the lifetime of the program. So So C solved the problem by getting rid of the nesting. First class is fine, non-local references are fine. And that was a pretty common compromise. Get rid of the nesting. Now, Pascal allowed nesting, allowed first class, and allowed non-local references, but they made restrictions on the nested functions. Then the compiler did what I just said a minute ago. They did restrictions on the nested, so they allowed restricted nested functions. The nested functions either could not escape or the nested functions couldn't make non-local references, one or the other. Some compilers were actually kind of clever. If the nested function made non-local references, then it wasn't allowed to escape. If the nested function did not make non-local references, then it was allowed to escape, but it couldn't make a non-local reference. Okay, so one or the other. It either made non-local references and so it couldn't escape, or if it was meant to escape, then it couldn't make non-local references. The Pascal language, it did it where nested functions couldn't escape. They weren't allowed to escape. Okay, so they were restricted in their first classness. So in Pascal, you had nested functions, but they were restricted to being nested functions weren't first class. Global functions were first class, but not nested functions. Okay, other languages, you had nested functions, but they couldn't make non-local references. Global functions could make non-local references, but nested couldn't. So C eliminates nested functions. Other languages allowed nested functions, but they limited them. They either weren't first class or they couldn't make non-local references. Okay, so you had all three: nested functions, first class functions, and non-local references, but the nested functions were restricted to being either not first class or they couldn't make non-local references. All right. So this is the structure. This is the problem that programming language designers faced. Unless you wanted to do more extra work, to allow all of these nested first class functions with non-local references, you had to do some extra work. Now there's actually a fourth ingredient here that I haven't mentioned, and that's lexical scope. I'm assuming here that everything is going to be lexical scope, so that this X is that X. What X do I mean here? The X that you have there. What Y do I mean there? The Y you have there. Because here's something you could do. You could use dynamic scope. If you use dynamic scope, this function's okay. Okay. At this point, that X and Y disappear. But now you get a global X and a global Y. So when you call G, which calls F, this X is not that X. This X is that most recently declared dynamic X. Okay. And this Y would be that Y. Okay. And that historically is how the Lisp people actually solved this problem, but they didn't realize that that's what they were doing. They solved this problem by allowing nested first-class functions that use non-local references, but they used dynamic scope, not lexical scope. So this X, you didn't really know what X it was. It was not necessarily that X. Okay. If you called the function here, if you did apply F to, say, 17 here, then you'd call F right away. Z would be 17, that X would be that X, and that Y would be that Y. But when you call G down here, you can't call F down here because F is out of scope. So the variable name F is gone, but the function's been stored in G, so you can call G down here. But now when you call G, the X here is that X, and the Y here is that Y. On the other hand, if you do this, the program blows up. When you call G, this X is gone, that X is gone. Oh, there's a new X, so this X is that X, but there's no Y now, so the program blows up. And Lisp programmers knew that they had these issues where programs could blow up because variables could disappear on you, but they just somehow it took them like 20 years to figure out what was really going on. Lisp was invented in the 50s, and this wasn't completely ironed out until the 70s. I mean, I'm sure there were people who really understood this even within the 20 years, but it wasn't until the 70s that this stuff was completely nailed down and made really rigorous. And so Lisp programmers knew that you could have functions that were stored in variables, and that the functions, you had to make sure that their variables that they needed were in exist. You had to make sure that when you called this function, that there were on the stack all the variables you needed. So G is a reference to F. F makes a non-local reference to an X and a Y, and it's up to me when I call G to make sure that there's an X and a Y somewhere. But that's horrific programming. Dynamic scope is considered a real mistake. It should be static scope. This X should be that X, and this Y should be that Y. Okay, so there's really 4 ingredients to all this. The 4 ingredients are you need lexical scope. If you use dynamic scope, then you can fudge this. Okay, so you need lexical scope, first class functions, and non-local references, and what was the last one? See, I keep first class. Oh, and nested. Okay, so you have to nest a first class function with non-local references using lexical scope. Then you need a closure. If you pick 3 out of any of these 4, you don't need a closure. Okay, if you pick 3 out of any of the 4, like if you do these 3, but with dynamic scope. So if you don't pick lexical scope, then the alternative is dynamic scope. So you have to have one or the other. You have to have either lexical scope or dynamic scope. But dynamic scope is bad. Okay. I mean, historically, they kind of stumbled into dynamic scope. Okay, but it's really considered bad. So you either have lexical scope or dynamic scopes. Dynamic scope's kind of what you get if you're not really careful about what you're doing when you write your interpreter. You get dynamic scope. They got it by accident and didn't really realize that that's what they were getting. Okay, so if you have any 3 of these, you're okay. By 3 of these, I mean if you have these 3 with dynamic scope, okay, or if you have lexical scope with any 2 of these, you're okay. But if you have all 4 of them, all 4 need closures. Okay, and that's what we want. And then we have to explain what a closure is. Closure solves the problem that you get when you go back here and you get rid of this, and you say what happened to X and Y. Essentially, what closures do is they keep X and Y hanging around. The key idea is to not let them disappear. When you get to here and this nested environment goes away, you actually don't want it to go away. That's actually the key idea. It's actually not a deep thing. The idea is, well, if it goes away, it's broken. So don't let it go away. Yeah. The environment that holds X and Y would normally be deallocated at this point. Okay, but if it's deallocated, then F loses its variables. So don't deallocate it. But how do you do that? How do you make it so that when this environment goes away, it doesn't get deallocated? Okay. Another way to put this is when a function returns, its local variables don't disappear automatically. Okay. So, which is very much against the whole notion of the way the C language work and the Java language work. When a function returns or when a block ends, everything in the block goes away. Okay, that's you're taught that over and over again. They're called local variables because when you get to this point, the local variables go out of scope, and usually we think that means they disappear. Now what it's going to mean is when you get here, the local variables got a scope, but they don't necessarily disappear. There's a way to make them hang around. That's what the closure does. Okay, the closure makes those local variables stay somewhere. Now they don't stay on the stack because you can't pop something off the stack and still have it on the stack. So you have to do something else. You have to do something a little bit trickier than that. And this is what they kind of finally figured out. But a closure is the mechanism that lets you not have these variables disappear when you get to the end of that nested environment. Okay, so you've got this begin environment, and you don't want these variables to go away. Okay, so that's what the close. But again, if you don't have all four of these, you don't have to worry about it. You don't need closures. If you don't have all four, lexical scope, first class functions, non-local references, and nested functions, if you only have 3 out of 4, you can get away with C. Okay, C has lexical scope, C has first class functions, C lets you use non-local references, C doesn't allow nested functions. Okay, and like I said earlier, other languages, they almost always have these 3. You really have to have those 3. A modern language can't get by. The alternative lexical scope is dynamic scope. Dynamic scope is horrible. Okay, very few people think that dynamic scope is a good idea. There are a small number of programmers who think dynamic scope is cool because you can do all kinds of weird tricks with it. But the vast majority of people think dynamic scope is a real mess and a mistake. So every modern language uses lexical scope. You need to be able to store functions and variables. We saw that with callback functions. Callback functions are very important. To have a callback function, you got to be able to store the function in a variable so that you can call it later on. So first class functions are really important, in particular just for callbacks. Non-local references are pretty much useful. It's nice to have a function make reference to, for example, some global variables. Okay, you could possibly get away with non-local references, but it'd be really hard to write a language where every function, like you couldn't write classes if you didn't have non-local references, because in a class, you do something like the point class. Remember how you would just the point class we have an double x, and a double y. Okay, then you're going to have a constructor. The whole point of the constructor is to make a non-local reference. This dot, well, actually, let me call this way. New x, new y. So then you say, the whole point of a constructor is to make a non-local reference. X equals new x. Y equals new y. If you can't make that non-local reference, how in the world is the constructor going to put a value into there and put a value into there? So you can see that the notion of a non-local reference is ubiquitous in the language. You can hardly imagine that you could do anything. Like, another one would be if you want to move a point, you'd move a point by an X amount and by a Y amount. What are you doing? You would say things like X plus equal by X. Move the point in the X direction by X and move the point in the Y direction by Y. Okay, you're making non-local references. See, in object-oriented programming, when you're programming classes, the whole point is that variable is up there. It's a non-local reference. Okay, you'd be hard-pressed to invent any modern language that doesn't allow you to make non-local references. Okay, so all of these are they're just ubiquitous. Non-local. Yeah, non-local references are almost unavoidable in modern languages. Okay, so first-class functions are a necessity in modern languages because of things like callback functions. That's just one example, but that would be a real good example of why first-class functions are a necessity. Non-local references are going to be pretty much a necessity. You couldn't do object-oriented programming without non-local references because you wouldn't be able to affect these instance variables in your methods. The whole point of instance methods referenced inside of methods is non-local references. Okay. Now, you could kind of fudge this by making somebody always do that. And then you could kind of argue that that's not really a non-local reference because you've given it a scope. You know. Now, JavaScript makes you do this. JavaScript actually does make you do this because JavaScript's kind of screwed up in a lot of ways. So you can't do that in JavaScript. You actually have to say this dot. But C++ and Java, you can put the this there or not. If you put the this there, it's not technically a non-local reference because this says it's the X in this object, but this is a non-local reference. But the compiler changes it to being this. The compiler rewrites it as this. Okay. Okay. So non-local references are pretty much ubiquitous. Okay. This is the thing that you don't really have to have. Okay. Nested functions, you can, Java doesn't have them, C++ doesn't have them, C doesn't have them. Okay, so that's the one that's the one that's the first one to get crossed off the list. You can't get rid of those. You pretty much have to have them. This guy, optional. If you do allow it, then you're back to what I was saying a while ago. Pascal said, okay, we're going to allow nested functions, but we're going to put restrictions on them. If a function is nested, it can't be first class. Okay, so for nested functions, only global functions can be first class, not nested functions. So we'll allow nested functions, but they're not first class. That's what Pascal said. Some other languages tried to play more games like if a nested function made a non-local reference, then it can't be first class. Or a nested function can be can make non-local references. Okay, well, yeah, if a nested function can be first class, but then it cannot make a non-local reference. Yeah, a nested function is allowed. It can be in first class, so it can escape, but it can't make a non-local reference. It has to be a closed function. It can't make a reference to any other it can't make any reference to anything but its own variables. Okay, so it's the four of these together that is the magic ingredient that causes a problem. Okay. Yeah. And like I said, by the time C was invented, this stuff was well understood, and the C designers said, okay, we're going to axe the nested functions, just no nested functions at all. Okay. You can't have functions inside of braces. Functions can only be at the global variable at the level. And Java pretty much did the same thing. Java doesn't have nested functions. It doesn't. But it has nested classes. You can put classes inside of classes, and that actually is very close to nested functions. And so Java is a little bit sophisticated. It kind of threads a needle between what C did and what these other languages did. Java doesn't allow nested functions, but it does allow nested classes. But that actually made Java kind of complicated. That's one of the more complicated aspects of Java. People get really confused about just what you can and can't do with nested classes. Because when you put a class inside of a class, there can be functions inside the class. And for example, in Java, I can put a class definition inside of a function. I can put a class definition in here. I can put a class definition in the middle of a function. Okay, that's allowed in Java. And then this class can have functions in it. Okay, the nested class can have functions. Now, that function is nested inside of that function, but it's nested inside of a class inside of that function. And there's all kinds of rules about what you can do with these things. Now you're kind of back to, well, if you're going to allow nested classes, now you're going to start making restrictions. And that's what Java does. So Java allows nested functions, but it kind of does what Pascal did. It started saying, well, nested classes give you nested functions, so we have to start making restrictions. So for example, you can make non-local references, okay, but they have to be to constants. And that's what happens. Java ended up with a weird set of rules where you can have nested functions inside of functions, sort of. You have the functions are inside of classes, the classes are inside of functions. You can take a non-local reference, but the non-local reference must be to a constant. It cannot be to a variable. It can only be to a constant. Okay, and so they started making all these restrictions. And a lot of people don't understand why the restrictions are even there, and they get mixed up about them. But it's really this thing here. You can't have all four of these unless you have closures. Okay, so when Java allowed nested classes, and the nested classes could have functions inside of them, they essentially ended up with nested functions, and they started putting restrictions on them. And the restriction came to, well, you could make non-local references, but they had to be to constants, not to variables. Okay, and if you read about nested classes in Java, you'll see that there's this little footnote a lot of times about how if the nested function in the nested class makes a non-local reference, it has to be to a final variable, because they don't call them constant, they call them final variables. So nested functions and nested classes have to only make references to final variables. Okay. Okay, but then it's tricky. For example, I think if I remember right, see, this class can have a, okay, this thing can make reference to, it can make reference to XXX because that's its own variable. But if this guy had a local variable, this guy can't do this. Okay, that's a non-local reference to his own variable. That's a non-local reference to the outer variable. This non-local reference is allowed. This non-local reference is not allowed. Now, if this thing is a final variable, then you can reference it, but you can't change it. See, the idea is you can reference it, but you can't change it. Then it's allowed. So this guy can make access to this guy's non-local variable, but only if it's final, and then you can't do anything to change it. So you end up with some pretty confusing rules in Java. Non-local references are kind of allowed as long as they're to your own variables. Non-local references are allowed to your outer variables, but only if they're final, so they can't be changed. And yeah, it's all about not having all four of these. Because if you have all four of those, then you need closures. And Java was designed not to have closures. The original design of Java didn't have closures. Now, the new version of Java does have closures. So some of these restrictions are going away. So Java is now allowing things it didn't allow a few years ago. So there's some things you can do down here. There's still some things you can't do. Like that, I think, still is not allowed. Yeah, this thing still has to be a final variable. But there are some things you can do now that you couldn't do before, because Java has something like closures. But if you understand these things real well, you can see where Java came up with its weird rules. The weird rules aren't that weird when you understand what's going on. The weird rules are trying to eliminate all four of these. Okay, so since you have nested classes, and the nested classes can have nested functions, then you're starting to approach all four of these. So they had to eliminate something. So they eliminated the non-local references to variables, but they allowed the non-local references to constants. And then they didn't have all four of these. Okay. All right. So that's the ideas involved here. That's what we're getting at is, in our, this demonstrates what can go wrong. Yeah. because it's using all four of the ideas. And you can kind of see, you have to remember that when you get to here, these go away, just like they would in Java or C or C++. Local variables are local. So when you get to the end of their block, they disappear on you. Okay? But then G, when it calls F, doesn't have anything to access. That's the problem. Okay. Solve it with dynamic scope by creating new variables X and Y here. But that's kind of cheating. Okay. But use dynamic scope, create new variables. That's kind of cheating. That's considered really sloppy. Okay. If you're not going to solve it that way, you have to solve it with a closure. Okay. So if it's going to be lexical scope, so this guy is that guy and no other X. That's what lexical scope means. That X is that X, because that's what it says on the page. To keep that rule, you have to somehow make this environment not go away. That's what the closure does. Oh, and it's called a closure because, see, this is this line of code makes a non-local reference. So as we said a while ago, that makes these free variables. But those free variables are closed by all that. See, those two variables close those two free variables. So by making this block hang around, it's keeping this function closed. So that's why they called it a closure. By finding a trick that'll make this block not disappear, I'm keeping this code closed. So it's called a closure. The trick that keeps this block from disappearing is called a closure. On the other hand, if I don't have a closure and this block is deleted, then this remains, these variables are free. See, they're not closed, they're free. And then something else has to close them by using dynamic scope and me generating variables as needed dynamically. Okay? See, those two variables now help close this thing. Now this thing is closed by these variables. But if one of them is missing, see, then I have a close. Then this guy's not closed over. We say that the Y is still free. There's nothing in this program to close Y. He's not closed by that guy because we're using dynamic scope, not lexical scope. So he's not closed by that guy. And this one's closed by this one, but this one's got no one to close him. Okay. Now, if I put a global variable here, notice how weird this is. This Y is this global Y. This X is this X down here. Neither of these are these. See, if I use dynamic scope, this is why dynamic scope can be impossible to read. Is this okay? Is it closed? Well, it's not closed by this because we're not using lexical scope. Well, okay, there's a Y here that's never going away. So yeah, this thing will be closed by at least that Y. Now, on the other hand, if I do this, now this guy is closed by the most recent Y. It would be closed not by that Y, but by the most recent Y, which it can be nightmarish to figure out what's going on in a dynamically scoped program. In a dynamically scoped language, it can be nightmarish to figure out what's going on because variables are closed by whatever was the most recent instance of that variable at runtime. What was the most recent version of that variable at runtime. In programs with like that, in programming languages with dynamic scope, people would do stupid things like declare global variables that would keep their program from crashing. There's always something to close off that X and Y, these two guys. That may not be what I want at runtime, but my program's not going to crash because there's always something to close them off. They would call these the default values of X and Y. So they would say, oh, X is defaults to that value there, and y defaults to that value there. Then if you want x to have some other value, now x is 5 and y is 9 when you call that function f. That was their way of thinking. You know, that the variables, these variables were dynamically scoped. You gave them default values at the start of the program, and then you would modify them as you went along, like this, and then you'd call the function when, and then x and y would be those modified values. And then if you deleted those, then x and y would be the default values. Some people thought this was a reasonable way to code. Modern languages don't, okay? So if you have dynamic scope, you can have first-class functions with non-local references and nested functions, but you got to be careful that you don't have your program blow up because one of your functions loses its closure. One way to solve that is to close everything at the beginning of the program. Just have a big block of global variables to close off any non-local references. And people used to code that way. Okay, that's not what people do in C, because C doesn't have nested functions. But Perl was like this, and some other languages were like this. They used dynamic scope, and they programmed in kind of odd ways. If they were using non-local, like some people just would not use non-local references, or they didn't use. A programmer in a language that had dynamic scope could just choose to never have nested functions. If you don't write any nested functions and all your functions are global, then none of these issues come up. Okay, so if you just choose not to ever write a nested function, then your dynamic scope is going to almost act like lexical scope anyway, because everything is going to be either global or, everything's going to be global. Okay, so some people would just not write nested functions. So if you have all four of these, you have problems, or things get complicated. If you get rid of one of them, things are straightforward. If the language has all of these and it's using dynamic scope, a programmer could just choose not to define any nested functions to keep their program from being crazy. But if they have dynamic scope and they use all four of these, you can write completely unreadable and undebuggable code. And people did. And people really did write code like this. Okay. All right. So now the next thing is, what do modern languages want all four of these? Okay. Without the dynamic scope. Modern languages want lexical scope, first-class functions, non-local references, and nested functions. And Java and C++ are trying to move in this direction. They're getting closer and closer to allowing all four of these. To do it, you need closures. Okay, so then the question is, what is a closure? Now we said it's something that makes this block not go away. Okay, it's a trick for letting this block not disappear on you when you get to here. Okay, the block would somehow. Now what we're gonna do when we save this function in this variable here, see, there's the name for that function. What's going to happen is when we save that function in that variable, right now we have that variable point to this tree in the abstract syntax length tree. If we go look at language 7, a value object holds, when it's a lambda, it holds a tree. The lambdas actually point to the code itself. That's what C does. In C, a function value is literally the address of where the code is. Here, the function value is the address of its abstract syntax tree. It's just a reference to the abstract syntax tree. So we're doing exactly what C does here. Our function values are pointer to the code. In our case, a pointer to the code is a pointer to the abstract syntax tree. In C's case, it would just be the address in memory of where the compiled code of the function is. Okay, so right now, what you store in F is a pointer to that abstract syntax tree, or in the C case, you'd store the address of that code. What we're going to change to is we're going to store in F 2 pointers, a pointer to that code and a pointer to this environment. See, when we did a begin, remember the begin block created a local environment. So we'll let F point at that local environment. That essentially will say that F carries with it the storage of its non-local references. Okay, so F will now be 2 pointers, a pointer to its code and a pointer to the block that holds its non-local references. Okay, and if we go now to what a value is in language 8, the lambda values are now pair. It's something called an IPEP pair. Okay, instead of value pointing at a tree, value points at an IPEP pair. See, that was language 7. Not a big change. It's a very tiny change. You go value L points at a tree. That's C-like. The value of a function, what you store in the variable. When you store your first class, your functions are first class, so you can store them in variables. What do you store in a variable? The address of the code. In this case, it's the address of the tree that represents the code. In a compiled language, it would be literally the address in memory where the code is. Now we store a structure, an IPEP structure, that if we look at what it is, it's just 2 references. It's just, see, there's the tree pointer, but there's the pointer to the environment object. So an IPEP thing is 2 pointers. It's the pointer we were storing here. It's the pointer we stored here, the tree, bundled with another pointer. So IP stands for instruction pointer. That's the tree. Points at the code, the instructions. Okay, that's the tree part. But then we add to it an EP pointer. The EP pointer is, see, the IP pointer is the tree. The EP pointer is this pointing to the environment. In a case over here, F would hold a point. F would hold a pointer to this lambda. That's the root of that tree. So F would point to lambda, which is the root of that tree, and F would point at the environment that begin created. When we enter the, if you go back over here to language 7 or 8, doesn't matter. If we go back to the evaluator and look at what begin does, remember, begin creates an environment. Find it down here. Here's evaluate begin. See, it creates an environment. That environment holds the local variables. Okay, what we're going to do is store that pointer to that environment in the closure. When we get to this thing here, we will store in F the pointer to its lambda and the pointer back at its begins environment. So we have to figure out a way to do that. Okay, now that means that F carries a pointer to this block of this environment. So that environment does not get garbage collected when we get to here. When we get to here, which would normally cause this environment to be deleted because it says it right here. When you get to the end of this code here, the local environment you created here just gets garbage collected because nobody else has got a reference to it. So in language 7, this thing just gets garbage collected when you get to here. But in language 8, there'll be the possibility that this thing does not get garbage collected because it might be that if we did like here, if we store F if we store a function in a variable, that function will then hold a pointer to that begin block. We have to write the code that does that. We have to be, we're going to carefully write it eventually. Well, it's written already. We're going to look at it. But in language 8, in language 7, you're guaranteed that this environment disappears. In language 7, there's nothing that can keep a pointer to that environment, so it disappears. In language 8, if one of these local, if you evaluate the code in the begin block, if any of the expressions in the begin block store a function, then what they'll store is an IP-EP pair, and the EP in the function will point to the begin block. That it'll point to this guy here. So this guy then will be preserved by the IP-EP pair. It's not a simple idea. It's a convoluted idea. It's why it took years for this to get figured out. It's not like this is drop dead simple. It's notorious. It's considered a notoriously tricky idea for people to get their head around. Closures are always thought by everyone to be a tricky idea. It's not complicated. It's like 3 lines of code, but it's something pointing to something that points to something else. It's multiple levels of indirection. That can make things tricky. It's something pointing to something that points to something. What I mean by that is F points at an IP-EP pair. The IP-EP pair points at an environment. The environment holds the variables. So you've got 4 levels of indirection. The function points at the IP-EP pair. The IP-EP pair points at the environment. The environment holds the values of the variables you need. So more levels of indirection than most people can keep in their head. If I don't think real hard about it, I've been studying it for years, I can easily get myself confused by this stuff. Okay, so it's not trivial because it's multiple levels of indirection. The function holds an IP-EP pair. The IP-EP pair holds 2 references. One of them is a reference to an environment. The environment holds references to variable value pairs. And so that's where you get your value. So the function points to the environment. No, the function points to the closure. The closure points to the environment. The environment holds the variables. Okay? Yeah. And then this thing works. Then there's no problem. G, when you assign F to G, you're assigning the IP-EP pair that F is to G. So G is an IP-EP pair. So it holds both the code to run and the environment to use. So when apply applies G, it's got to do 2 things. It's got to jump to the code, which is this code, but it has to evaluate it using a pointer to this environment. So G needs both those things. It needs to know what code to execute and what environment closes the open function here. See, G will hold a pointer to that code, but the code is open. So G needs a pointer to an environment that closes off those free variables. So G's got to point to 2 things. And that's what the closure does. G points to where the code is, what environment closes the code, and makes the 2 variables close off those variables. So they're not free. If you only point to the code, you're stuck with free variables. Okay? And they've got to get closed somehow, or your program blows up. And then you're back to, well, you can close them using dynamic scope, but we don't want to do that. We want to close them lexically, but then that means that G's got to know where to find the object that holds X and Y. Okay? All right. So now let's see if we can actually trace through the code that does that. Okay? So we've explained it in words. Let's see if we can actually trace through the code that does that. There's 2 steps involved. When you define F, you got to create the closure. When you call F, you got to use the closure. I'm sorry, when you call G, you have to use the closure. Okay, so the closure is created here. The closure is used here. Okay, so there's got to be a sense of something that can create a closure and something that can use a closure. Apply is the thing that uses the closure. Okay, the lambda is the thing that creates the closure. We're going to see that it's going to be lambda that, let's look at creating the closure is the trickier part. Using the closure is the easier part. Actually, let's look at the easier part first. Suppose the closure has been created somehow. So G points to both the code to call and the environment to use. Okay, so go over here to the evaluator for language 8. And look up apply, which uses the closure. What's actually interesting is to compare this apply to the language 7 apply. See, this language 7, this is language 8. The applies are going to be very similar. There's like a little bit place where there's a little bit of difference, where language 8 uses a closure and language 7 doesn't. Okay, here's apply in language 7. Here's apply in language 8. If you compare them, oh, let's see, let's see. There. If you compare them, you'll see there's not a lot of differences. Oh, I forgot to update the website. That's funny. I thought I updated this. There's actually fewer changes than that seems to. Boy, I could have swore I updated that. I rewrote the evaluator to language 8 to make it look as much as possible like the language 7 evaluator. And I did that the other day, and I thought I uploaded that. Maybe I forgot to upload everything to the website. Okay, I probably just forgot to upload the changes. I purposely rewrote the evaluator to language 8 to make it look as much as possible like language 7 so that you could see what changed. Like right now, it looks like a bunch of changes, but there's really not that many changes. Boy, let's see. The big change is step 3 here, changes to step, well, this is I'll put the new one up there, but this is step 3. Step 3 is the main change. This step 3 replaces this simple step 3, and then pretty much everything after is the same. So like if you go start here with step 4, there's going to be almost the same thing. And I just have to kind of yeah, if you write it carefully, you can get it so the code for language 7 and the code for language 8 line up. Like I almost got it lined up now. I think it is lined up now, almost. Yeah, almost lined up. And you can get them, and you can see that there's not big changes. It's pretty small changes. Like this is supposed to be final. This is supposed to be final. This one's final. You can see there's less and less changing. Some of the comments, little things like I wrote a comment here and I wrote a comment here, and I changed it so the wording was the same in both comments, because it's actually the same. Like this comment here actually is saying the exact same thing as over here. I just got the wording. Yeah, I made it so that the wording was exactly the same, because they're really saying the same thing. Okay, and there's a couple other places where I'll after class I'll make sure I'm sure I did this 2 days ago, and I probably just forgot to upload the new version to the website. But I made the evaluate in language 7 and the evaluate in language 8 look as much alike as possible, so you could switch between them and you could see what was changing. And it should be the only real change is step 3. If I remember right, the only thing that changes is step 3. This step, because this is the step that uses the IP-EP pair. In step 3 here was get the tree. Now you have to get the tree and the environment. So where Here it was go get the tree for the function. Now it's go get the tree and the environment for the function. And then this other change is to use that environment instead of the default environment. So you start farther down here, you start using that environment. Okay, instead of using this environment, you use this environment. Okay, you evaluate the body of the function using this environment here, and that means if you think about over here, when you evaluate the body of this function, you have to evaluate it using that environment. So that's where it changes. You evaluate the body of this function using that environment. So there's going to be a change in 3, and there'll be another change down here where you just change what environment you're using. Okay. So that's where we'll pick up on next week. Okay. So we'll finish this. We'll finish comparing language 7 and language 8 for the, okay, first, we're right now we're comparing evaluate, apply, and we'll see that there's just a minor change. Use the IPEP pair instead of use the combination of the code pointer and the environment pointer, whereas language 7 used only the code pointer, the tree. Language 8 needs the tree and the environment. Okay, so that's one little change. And then further down, you'll use this environment in one step, where before you were using this environment. Okay. All right. So there'd be just like 2 minor changes. And then the bigger change is going to be where we create the closure. That's the little bit harder part. That's here in this line of code. When F is created, you have to create a closure instead of creating just a lambda expression. So we'll look at that. And then that's the difference between language 7 and language 8. The profound difference amounts to about 10 lines of code. Out of an evaluator that is now up to 800 lines of code, the change from old-fashioned C to modern functional programming means out of those 800 lines, you change about 10 or 12 lines. Okay. Now you also have to define the IPEP status structure, which isn't much. You define that IPEP data structure. You change 1 line of code in your environment, in your value. Change 1 line of code here. Define this 10-line class. Then make a few lines, just change a few lines of code in the evaluator. And you've made you got a PhD thesis out of this. You become world famous for making these few little lines of code. This is actually what's beautiful about computer science. Somebody became world famous for making all these little changes, like a small number of little changes. And now we know how to see it. Now we can abstract it and see it beautifully. It took a lot for them to figure this out. But now we can see that, boy, they just made a few small changes, and they revolutionized computer science. Okay. Because the jump from language 7 to language 8 is going from C to modern functional programming. That was the big jump. And now we see that it's really just it's a few small changes in the value, in this, and in the evaluator. The changes altogether don't amount to 15 or 20 lines of code out of 1,000 or so lines of code. But profound, subtle, big ideas lurk in small changes. Okay, so we run out of time, so we'll finish these ideas on when we come back on Wednesday, on Monday. Okay. Anybody got a question? Any kind of question? Read this code. I mean, the code is actually pretty documented. So I'm explaining things in class. There's no real good textbook that explains these ideas. This is kind of considered graduate level material. They don't put this stuff in books. It's documented on some websites, but every website does things its own way. So like we're writing it in Java. If I point you at a website that explains this in Haskell, it doesn't do you much good. Or if I point you to a website that explains this in C++, it doesn't do you much good. So like there are good explanations out there, but there aren't any good explanations that do it really well in Java. I mean, there is that one book we're using for the class, but we kind of he still does it a little bit differently than what we're doing it in here. And so like, the course does have that one book. This is explained. You might get some value if you want looking at his, he does explain these ideas here in chapter 10, you know, but he's got his own, see, there's the lambda expression. He's got his own way of explaining it. It is explained in there, but it's explained relative to his code. And his code is structured a little bit differently than our code is, but he covers all the same ideas. So yeah, he does talk about these things. Forget where function declarations. Eventually he gets to talking about closures. I think this is, you know, notice how long this is. There's a lot to explain. Yeah, there's local functions and closures. Local functions, he means nested. Yeah. So there's where he talks about, okay, nested functions, and we need closures now. So he kind, it's in here, and the code is more or less equivalent to ours, but it doesn't look exactly like ours. So I haven't given you reading assignments here because I thought it kind of our code diverges a little bit too much from his code. Unless we used his code directly, it's kind of hard to, you can try reading it. You might find it helpful. Yeah, maybe if you can make the connection between his code and our code, because eventually that's what you need to do. Not everyone's going to write things. We're talking about the ideas. He wrote one implementation of the ideas. We're doing another implementation of the ideas. It's still the same ideas. So the fundamental ideas are the same. There's two different versions in Java, his version in Java, our version in Java. There are other websites that do it in Haskell, others do it in ML, some do it in JavaScript, some do it in C++. There are lots of explanations, not a lot. There's a few out there. There's no textbook that does this that I know of. I don't know of any textbook that does this really well. None. So there's some websites and some papers. I don't know of any book that does it. But it's the heart of modern programming. Okay? It's really the heart of modern of modern programming languages. But it's graduate level material. Graduate level computer science material isn't usually in books. It's in papers and in websites. Okay. All right. We'll quit there. So we'll finish closures on Monday then. Okay. All right. So I'll stop sharing. Have a nice weekend. Bye.